The search for life beyond our Earth is a daunting prospect, and yet the signs of building blocks are everywhere.
I can't say for sure because we've only got the one example of life on Earth to work with so far, but all the ingredients are out there. Solar systems make everything you need for life, insofar as we know. So it could be that matter naturally organizes itself into life.
Within our solar system, we are studying all the places where life might well evolve. Mars, for example, once had two of the essentials, free-flowing water and volcanoes. Then there are the ice moons of the giant planets, Europa and Ganymede, with their internal oceans. Even the far-flung Pluto has shown some interesting signs. There is, however, only one ideal environment in our solar system, Earth. To find other such oases, we must look for exoplanets around other star systems, a very difficult challenge.
Well, there's sort of two things that are driving the places that we look for exoplanets. The planetary systems where we'd most like to be able to find planets just like our own, that orbit at just the right distance from their host star to potentially be able to host life, are orbiting stars just like our own. So they're what are known as G-type stars. But the difficulty is that the distance that a planet orbits around one of those stars, with a period of around 1 year, means that the signatures for seeing those planets are really, really small. So they're incredibly technically challenging to find planets around Sun-like stars. So the next best category, the sorts of systems that we're putting a lot of effort into, are stars that are much smaller than the Sun, about a tenth the size of the Sun. You get a type of star that's called an M-dwarf. It's very red, it's very faint, and as a result, the distance where you get the same amount of flux as you get from the Sun shrinks in to about the orbit of Mercury, or inside the orbit of Mercury. And that makes the signatures for detecting that planet much easier to find. And so there's a lot of effort going into looking for what we call habitable zone planets around these small M-dwarf stars. There are two basic ways that we can find planets around other stars. And both of them look for the indirect effect of the planet on the star. We don't see the planet itself, we see what the planet does to the star. And we either see the planet orbiting within the line of sight and crossing the disk of the star and making it a little bit dimmer. Those are what are called transit planets. Or we see the planet orbiting around the star and making the star move backwards and forwards along the line of sight. And we can measure the velocity of the star. Basically, we use telescopes as giant speed guns to measure the star going backwards and forwards. And those are what are called Doppler detections of these planets. And for transit searches, finding multiple planets is a lot easier. Most of the multiple planet systems we've found have come from space-based transit searches like the Kepler mission. For Doppler searches, finding the subsequent planets gets harder and harder and harder. As you go to larger and larger separations from the star, the wobble signature of the star moving backwards and forwards gets smaller, and it gets progressively harder and harder to find. So what we found is that there are lots and lots of multi-planet systems out there. I don't know that it's true that they're less or more common than we at first thought. They require more intensive observations. When you're looking for a planet around another star, the first planet you find is the easiest planet to find. And then finding the subsequent planets usually involves getting more and more and more data so that you can see usually the much smaller signal on maybe a longer period that tells you there's another planet. And then once you found those two, if you want to find a subsequent one, then you've got to get even more data.
To this end, 2 new space observatories are soon to be launched. TESS, NASA's Transiting Exoplanet Survey satellite, designed to find planets crossing the face of their sun, and the much-lauded James Webb Space Telescope. It will be able to see and analyze the atmospheres of those distant planets.
So we have 4 key contributions. We are supplying 2 out of the 4 scientific instruments. We are responsible for the launch of James Webb from French Guiana with the Ariane 5 rocket. And we also supply personnel for the operation of James Webb Space Telescope from the Space Telescope Science Institute.
So James Webb has been built initially to see galaxies and when they form. So the galaxies are this assembly of stars. And we are trying to look at really the first 100 million years of the universe and look at their formation. But at the end of the day, it's going to do much more than that. And in particular, a very exciting field where it will do a lot of, bring exciting results, are exoplanets, characterizing the atmosphere of planets orbiting over stars. That's really exciting.
TESS and the James Webb Telescope will be ready for launch within the year and are expected to open up a whole new era of discovery.
So there are the things we expect Webb to do, such as see the very first stars and galaxies to light up after the Big Bang. So we know we've designed it for that. We expect it to do that. Additionally, we expect that people will use it to study the atmospheres of exoplanets. But as a scientist, what I look for are those unique uses that no one has planned for, because it's out of those unexpected discoveries that most of the excitement arises.
To date, there are over 3,500 confirmed exoplanets, double that again yet to be confirmed, and of those over 360 are terrestrial planets. Some are even classed as super-Earths.
The reason why the TESS mission is exciting compared to, or in addition to Kepler, is that Kepler has told us an enormous amount about the statistics of how many planets are present around stars. So it tells us that the frequency of very small planets is quite common. So planets on around about the sort of the size of the Earth seem to exist around almost every star as far as we can see, often in very short periods, much too short to be habitable, but they're relatively common. But what it doesn't tell us about is the properties of those planets. So because when you find a transit planet, you're essentially seeing a dark thing moving across the disk of a bright thing. The only thing that transit detection tells you is about the period of the planet and the size of the planet, is its physical radius. What we really want to know is the size of the planet and its mass. Because if you know the size and the mass, then you know the density. And if you know the density, you know whether it's a gassy planet like Jupiter, or an icy planet like Neptune, or a rocky planet like the Earth or Venus or Mars. Before we found exoplanets, before we found planets around other stars in 1995, everybody expected that planet formation elsewhere would produce systems that look just like our solar system. And for about 20 years, what we consistently found was thousands of planetary systems that look nothing like our solar system. We've got gas giant planets that orbit inside the orbit of Mercury. You've got gas giant planets that orbit where Venus, Earth, and Mars are. You've got planets in highly eccentric orbits, highly non-circular orbits. Almost all the orbits in our solar system are really quite circular. Most exoplanets, most planets around other stars, don't have those nice circular orbits. We find system architectures that are very, very different from our own, which suggests that maybe the structure of our own solar system is not the norm. Maybe it's unusual for reasons that we still don't understand. Planetary system, even just the Earth, is an incredibly complex system. And we are yet to understand the sort of multiplicity of what other planetary systems look like. The other thing to bear in mind is that saying that other planetary systems should look like our own solar system is an incredibly risky assumption to make.
The variety of planets we are finding is indeed fascinating, from hot gas giants of various sizes to terrestrials varying in dimension from moon size up to 2 or 3 times the size of Earth.
So, finding planets is hard. It's really hard. Finding life is that much harder still. At the moment, the prime focus of most of the people who are looking for planets around other stars is not so much to look for signatures of life, but look for signatures of habitability. That is, an environment that is similar to what we see here on the Earth. So, a roughly Earth-sized planet at roughly the same sort of separation from its host star, modulo the brightness of the star. And then potentially saying, well, can we see the properties of the atmosphere? Can we see whether it's got water in it? Can we see whether it's dominated by thick clouds of sulfuric acid like Venus, in which case it's probably not going to be habitable, or has it got a relatively thin atmosphere like the Earth? The Earth's atmosphere is actually quite tenuous compared to the atmospheres of lots of planets. So it's sort of finding out those properties. That's even harder. The next step is what are the signatures of life that you look for? Do you look for methane emissions? Do you look for the signatures of molecular oxygen? So when the Earth first formed, there was no molecular oxygen in the atmosphere. Oxygen is a byproduct largely of life, of the cyanobacteria that formed in the oceans very earlier on. So those are the sorts of signatures that you could try to look for. A lot of that is sort of guesswork because we don't really know how life on our own Earth got started. Trying to guess what life on another planet would look like, we're sort of limited to looking for something just like ourselves. There's no guarantee that the only pathway for life is to look just like us.
The visible stars above us at night most likely all contain planets, and not just one. The keys to confirming these discoveries are highly sensitive spectrographs here on the ground, like the European Observatory that uses the extremely successful HARPS.
So we're building a new facility to do the Doppler follow-up that I was talking about before. You need very specialized pieces of equipment attached to very large telescopes to do this. If you remember, because planets are small, stars are big, the wobble that is produced by a planet going around a star is very small. Jupiter produces a wobble in velocity of about 12 meters a second. So it makes the sun move at about the speed of Usain Bolt. and it does it with a period of around about 12 years. Now, measuring the speed of Usain Bolt sounds straightforward to do, except that you're trying to do it around something that is extremely faint and somewhere between 50 and 100 parsecs away. And so you're having to calibrate your system to extraordinary levels of precision. That's to find an easy planet like Jupiter. If you want to find a tiny planet like the Earth, you've got to get down to precisions in the velocity that you're measuring of well below a metre per second. And that's why we need to build specialised facilities to go on our telescopes, like the Veloce spectrograph, which sits in basically in a big box. It's pressure controlled, it's temperature controlled. It's got a state-of-the-art laser comb where we pulse a laser with extremely high precision to make a calibration signal to inject into it. And you need a big telescope, at least a 4-metre telescope like the Anglo-Australian telescope, or bigger ones. Similar facilities are being built on 8-metre class telescopes and larger. So the European Southern Observatory have been running the HARPS spectrograph on their 3.6-metre telescope at the Lucia Observatory in Chile for over 10 years now. And it is, again, another one of these ultra-stabilised, very complex spectrographs. We have adopted for Veloce slightly different design strategies in a number of different ways because we have a different site and a different telescope. But it is focused on very much the same sort of science, and it, along with us and a number of other facilities worldwide, will be engaged in the big international endeavour of following up the results from TESS. One of the things that Kepler taught us, it found thousands of exoplanets. And when they started that mission, the follow-up programs were essentially limited to just the people who were in the TESS science teams. And they quickly found that there was not enough telescope time available to them and not enough telescopes in order to exploit the treasure trove of data that came out of Kepler. So we've learnt from that. The TESS mission, the data is essentially freely made available once it's been processed by the TESS team. It's put on a website, and then everybody around the world will be trying to coordinate, but also trying to compete to find the most interesting planets coming out of that. The main point being that there is so much data, even using all of the telescopes and all of the facilities available to us, there will still be objects which don't get observed and don't get followed up. So we and HARPS will be both competitors and collaborators in following up the results from TESS. And of course, the interesting thing is that for almost the first time in the history of modern astronomy, Southern Hemisphere chauvinism has been reversed. So TESS is surveying the Southern Hemisphere first. So we get first dibs on all of that data ahead of those Northern Hemispherites.
With the new technology about to come online, the speed and success of planet finding and confirmation will increase considerably, allowing us to better target the planets of most interest to us. Planets too close to their stars, stripped of atmosphere. Solar flares sterilizing the planet's surface. Terrestrials baked in unforgiving sunlight. Planets beyond the habitable zone, icy or frozen. A planet entirely covered with water is another possibility.
And what we're working on is better understanding that origin of life setting. What is the chemistry required? What are the interactions that make the steps to get to complexity? Do you need 100 fields? Can you do it in one? What are the other? So there's a whole field of investigation that's building about understanding Darwin's warm little pond. He foresaw this 145 years ago, and we're now just finally catching up to his prescient insight and really starting to try and scientifically address that. And that is very exciting. That's what excites me in the morning.
From Darwin's warm little pond come bacteria, then algae, perhaps a world dominated by algae.
Yes, well, if you a product of science fiction is that we all assume that that other planets should end up looking more like our own, except maybe the grass is a different colour and a different shape. In practice, because we understand so little about how life got started here on the Earth, it's incredibly hard to understand whether that situation holds or not. And it makes for, fascinating literature and a great discussion to have down the pub, but it's not science yet.
What if eukaryotes diversified differently than on Earth, branching only 3 or 4 times, never seeding the world of animals, plants becoming the dominant life form?
So what we expect to find on other planets, in some ways we don't know that they'd be different in the broad view, because organisms still have to be able to do the same things. They have to be able to get energy, they have to be able to get nutrients, convert all those to useful products, and they have to be able to reproduce. So organisms are always going to have these characteristics, and we are confident that in order for animals or any organisms to become more successful, there has to be some sort of natural selection. So the way natural selection works is that you have variation amongst individuals. There are many more individuals that are made that can survive in the environment. Those that are better able to do their job have more kids, and we start moving along that trajectory of accumulating adaptations, things that they're able to do better than others outside. So these basic processes are going to be what drives the change in life over time. Well, there's a lot of basic physical conditions that are going to be common throughout planets and the life forms that evolve on them. And so being able to sense distance, I guess, is one of those things. Could you get better depth perception with more than 2 eyes? It's hard for us to tell. Well, so many animals have many more than 2 or 3 eyes, and it depends really what you want your eyes for. So there are lots of organisms that have very simple eyes. Say a jellyfish has light-sensing organs that go all the way around its body, and these are able to help it move towards or away from light. But if you want to be able to actually form images more than just light sensing, these are structures that have to be evolved, and they take up more space. They presumably also take some degree of brain power to be able to process that image and make them useful. So if you had only 2 eyes and they could basically see 180 degrees or more than that, is that ever going to be, are you ever going to need more than that? But we always know that the further apart you put the eyes, the better your depth of perception will be. I guess one of the things that might be advantageous of having multiple eyes is that you could have different eyes that do different things. So there are some fish that spend most of the time underwater, and so to make it so that eyes work well underwater, you make your optics, the lenses, act well underwater. But then if the fish wants to look above the water, the optics are all different, so they can involve separate eyes or separate parts of eyes that are designed for looking through air rather than through water. So having multiple eyes that do different things would be an advantage.
How about mobility? How many legs are best?
Two legs is pretty unusual. So two legs is not an advantage for most of the situations because they're quite unstable. And so it takes us more effort to be able to stand on two legs. We're more unstable, more likely to be knocked over. If we run on two legs, we're more likely to trip and fall than an animal with four legs, where you can have additional points of contact with the ground. And running fast is actually easier with four legs compared to two, with a galloping gait rather than a running gait. But when we look throughout the animal kingdom, we have a lot of different diversity in the number of legs, if we're talking terrestrial animals. And we know that more primitive arthropods like millipedes and centipedes have dozens of legs on their body, but arguably more successful groups like insects have said 6 is enough for me. And so they have sort of set their body plan to say, I only need 6 legs. I can do a lot, I can change those to do different jobs, but with those 6 legs, I can become the most diverse group of animals that we've ever known. There are other variations on that. You get spiders that have 8, you have crab-like animals that have 10. So part of the decision of how many legs you have is how adaptable can you make any of those legs. If you do have lots of sets of legs, that's going to limit some things that you can do. If you're always going to have a long, thin body with lots of similar legs, you won't necessarily be able to make big, strong claws for doing particular jobs. You won't be able to change your back half of your body to fit all of your digestive organs or your reproductive organs, which is what insects do. They've taken all their legs off their abdomen, then they have this large structure that it's not filled in with all the muscles and joints of legs. They can now put a lot of their organs in those. So in many ways, getting rid of some legs is useful. Well, we know that looking at animals now, we're looking at a tiny fraction of the total diversity of life that has ever existed on Earth. So we have a very biased view in what we think is possible. But looking back in the fossil record, we can see that animals that in some ways defy description have existed. We don't know exactly how they lived, and we imagine that many of these were sort of evolutionary dead ends. They tried something out. It was successful for a while, but something outcompeted them, something ate them to extinction, and extinction events themselves will have taken portions of that diversity away.
If life were well established on a distant planet, filling every possible niche, would it suffer extinction events similar to those that happened here on Earth? Is that in fact necessary for evolution to produce a technologically advanced intelligence?
Probably the very earliest extinction event that occurred on Earth was what's called the Great Oxygenation Event, where basically the Earth converted from what was almost entirely an anoxic environment, so there was no oxygen available, into something that's highly oxic like it is today. So oxygen started to emerge in the atmosphere. And it's thought that this process occurred because basically single-celled organisms called cyanobacteria first started to evolve. And what these do is a process called oxygenic photosynthesis, which is basically where they fix carbon using light, and they generate oxygen as a byproduct from this. So they basically perform a very similar function to what plants do.
The majority of the history of life has been single-celled organisms. So we know that it was very difficult for organisms to get past that.
Earth has endured 5 mass extinction events in her history. There is a case for saying that we humans are the direct result of those events, which were catastrophic for other species.
I think we would definitely expect that if the formation mechanisms of planets on other stars, around other stars, are similar to the solar system, then yes, you would expect that there would be impacts on other planets in the same way that they've been here on Earth. One of the important things to remember is that not all of the extinction events that we've had here on Earth are believed to have been mediated by impacts. Some of them have been mediated by global climate change, sort of snowball Earth events, which are thought to have had more to do with where the continents and the plates are on the Earth, and therefore where the snow and ice formed, and how the feedback processes changed from us having our the current environment to a much more tropical environment, much warmer planet, which we've had in the past, to much colder planets, which we've also had in the past.
One thing we do know about evolution is that, there's a certain number of available habitats. And when they get filled up, life doesn't actually need to evolve very much because it fills those habitats. So, the dinosaurs and that community was around for 150 million years. They were pretty successful. They filled up essentially all the different niche space with the plants and everything else and stuff, and the pterodactyls in the sky. And it took a meteorite impact to break that effective filling of the niches.
After that time of around 66 million years ago, when this major extinction event happened, there has been phases of cooling of the Earth. And perhaps that would have greatly affected dinosaurs in different ways from the extinction event. And that's one of the things that mammals have been able to diversify into, is this change to a cooling Earth that increased body size and furredness has enabled them to fill those roles.
And so these extinction events, these impacts or giant volcanic events that change the atmosphere and stuff, they're almost like wiping the slate clean and you can start over again. And so then life adapts very quickly during those change periods and fills that niche space again, but it does so in a different form. And that's where these evolutionary steps are able to develop. And at each step you could argue that there's increased complexity, but one of the things we're finding out is that we're not alone in being intelligent, right? Dolphins are very intelligent. They're the top predator in their niche space. There's all this incredibly complex interactions between predator-prey and, building up chemical arsenals. And it's just incredible what happens on a daily basis. And so you could argue that development of intelligence is an inevitable consequence of increasing complexity and development through time, whether it's in the form of a human or a porpoise or a dragonfly or something, Once they have to figure out ways to solve problems to be competitive and develop the right tools, then there's that possibility of developing great complexity. Because you and I, and really all life on Earth, is just a matter of organizational principles. It's really just complexity, right? So we're able somehow to stand on 2 legs, whereas most walk around on 4. But that's an adaptation to environment with this changed niche space. So, You could argue that if you let that experiment run again and again and for longer and longer, that you would probably end up with something that has intellectual capability in terms of problem solving. And we know that now. We know many animals, even spiders, use tools. So, we're finding we're less and less unique, but the level of complexity and adaptability is certainly, at a very high level in humans. And time is a great friend, Time gives you that ability to complexify. But the extinctions, maybe they were a really critical marker in terms of allowing this form of complexity to develop.
Other considerations when it comes to exoplanet environments have to include differing gravity, atmospheric density, and planetary spin around the star.
Within a reasonable degree of changing gravity, I don't think that it would have a big difference. Only with a massive change in gravity would I think things were different. But if, say, you decrease the gravity a lot, that would make flight easier. So maybe you'd find many more animals that are flying or gliding than we do on Earth. If you made gravity stronger, you'd probably decrease the frequency of flight because it takes more energy to be able to overcome that force of gravity.
What about size? Would differing gravity create larger creatures?
Depends in part if you live in the air or underwater, because when you live underwater, you are supported a lot more. So the largest animals that we've ever known live in the sea. They're the blue whales, and so their skeleton and their limbs don't have to be able to hold their entire mass. For living on land, there's some that suspect that the maximum size of vertebrates that we've seen, which include the dinosaurs and some mammals are still relatively big according to that. We think that their body size was not limited by the mechanics, it was by being able to get enough food to feed a very large animal. So being able to find a high enough energy food source and being able to move over the environment to get that seems to have been one of the major factors that limited their maximum size. So we think that they could probably get bigger, but they'd have to be able to feed themselves and have a big enough population to sustain themselves over a long time. If you had a very fast spinning planet where you're changing from night to day very frequently, you would get less specialization in animals that do stuff at night and animals that do stuff during the day. I would expect they would just be adapted to exist throughout that whole night-day cycle. And then if you go the opposite way, where you have a planet like Mercury where the same face always faces the sun, it's possible that it's way too hot on the side that faces the sun and way too cold on the other. And we might imagine that there's some sort of lovely habitable zone, but in that small gap between them where all life happens, and they then only have a single night-day combination for the whole of their life.
In 1961, astronomer and astrophysicist Frank Drake came up with an equation to determine the number of intelligent extraterrestrial civilizations that might exist in the Milky Way at any one time. Several factors of the equation are highly conjectural, leaving a great deal of uncertainty about the answer.
So the Drake equation essentially combines together a bunch of different uncertainties. It breaks the problem of, do we think that there's intelligent life out there in the universe that could talk to us, down into a series of terms. So there's a term for the rate at which stars form in our galaxy, which we actually know reasonably well. Then there's a term for the rate at which stars have habitable planets orbiting around them, which we're starting to get a handle on. It's probably, somewhere between 1 and 100% of stars. And then there's a term for the time it takes life to evolve, which frankly, we've got almost no idea about what the mean time is for that happen. We think on Earth, it took somewhere between 100 and 500 million years for life to first get started. And then there's the rate at which intelligent life forms. And we have absolutely no idea. We have absolutely no idea how you go from the time scale to go from bacterial life or pre-bacterial life to multicellular life, to eukaryotes, which are multiple cells all living together. And then you get to multicellular organisms. And then, so we don't know how long or how common that is. And then there's the whole, how long does intelligent life last? And we have no idea about that. So there's a few terms in the Drake equation that we know. The rest of them are essentially completely unknown. And when you multiply together a whole bunch of completely unknowns, you've got still completely unknown. So we really don't know. It's a handy way to think about how difficult the problem is, and it reinforces that the problem is incredibly difficult to understand.
Yeah, that's the million-dollar question, isn't it? I think there's two components to that, probably. So the Drake equation has 9 components to the equation, I think, something like that. And each one of those has a lot of unknown variables. So, you know, if you say you're off by a factor of 100 in one of those variables, and maybe one of the variables is actually, you know, how many stars are in the universe, we might be off by factors of billions. If you have 9 variables and you add those all up, that's a big numbers game. The other thing is that we occupy a very particular time slice. And so, you know, if you think of our capacity to generate a radio signal that can be beamed across the universe, that's an infinitesimally small sliver of time, right? We've had an advanced society since 200 years or something or whatever. And it's nothing. The universe is 13.7 billion years old, right? So what's the chance of being at the right place at the right time to intercept a signal that sweeps by 200 years, right? So it's just a numbers game.
Beyond our solar system, the next location for habitation is our nearest stellar neighbor, Proxima Centauri. Here, several planets have been detected, some in the so-called habitable zone around their star. Sending a probe to the nearest exoplanet is a daunting challenge, but not impossible, even with today's technology.
So even getting a probe accelerated up to 1/10 the speed of light would be extraordinarily technically challenging. And that would then take 40 years to get to Proxima Centauri. The difficulty being that it would have to be extremely small to get it accelerated up to that velocity. And so it's not entirely clear that it would have a big instrument package on it. The other problem is that it wouldn't actually contain probably an engine that would enable it to slow down. So it would essentially fly through the Proxima Centauri system at 1/10 the speed of light. And so it would essentially take a bunch of pictures very quickly and try to send some information back, and then you'd have to wait another 4 years for that information to get back. Look, I think it's an interesting idea. Whether it's a cost-effective use of our time, I'm not entirely sure. I think probably rather than trying to work out how to make a very small probe accelerated up to that velocity and then fling it at Proxima Centauri would be developing the techniques for building space-based, the very complex space-based telescopes that would enable you to block out the light from Proxima Centauri and try to actually image the planet itself, to do direct imaging, unlike Doppler wobble, unlike transit searches where you're only seeing the star and the effect the planet has. Try to actually see the planet itself, then try to get spectra of that planet to understand better what's actually going on its surface.
It appears, with all the evidence at hand, the sum of the Drake equation would currently be 1+. We are the 1. The plus is the possibility of technological intelligence within our stellar neighborhood of 1,000 stars. The odds are not good. It's not a question of the available environments, of which there are many. It's to do with the timing. Our time slice within the immense age of the universe may well leave us bereft of company for thousands of years, before our emergence and after we are gone.